All right, so maybe this is the easiest proof of square root 2's irrationality. Basically, when we talk about irrational numbers, it can't be expressed as a fraction. So we know something like the square root of 4 is 2, square root of 9 is 3. These are all nice whole numbers. We know the square root of 2 is approximately 1.41, blah, 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 goes on forever. But we want to prove that it can't be expressed as a fraction. And so that is our job today. And I reckon this is the nicest and most beautiful way that I've seen. And it comes down to factor trees, maybe just because I like them because they're so visual. But let's go back a step and think about some factor trees you might be familiar with. If you look at a factor tree for the number 36, now 36 is a perfect square because it's 6 times 6. And then each side of the factor tree can be broken up into 2 times 3 and 2 times 3, right? So every prime appears an even number of times. And this is something sort of maybe I didn't know, but for perfect squares, every prime appears an even number of times. So another example would be 100, which is 2 squared times 5 squared, which is obviously 4 times 25. Again, all the exponents are even. I encourage you to pick another square number, and you'll find that you'll get an even number of prime factors. So our key insight here is that squaring doubles every prime exponent. So p squared always has all prime factor exponents even. So you're probably wondering, what does that have to do with proving that the square root of 2 is irrational? But we will get there. So just a quick recap, what is a rational number? Rational number can be expressed as p over q, where p and q are integers, and q is obviously not 0. And we know that p over q is in lowest terms. So what that means is it's simplified fraction. There's no other number that goes into it. I think it's called their co-prime is the technical term. So we can always write p over q in its lowest term. They share no common factors. So for example, 6 over 4 wouldn't count because that's 3 over 2. So 3 over 2 would be lowest terms there. And so our proof strategy here is to assume that the square root of 2 can be expressed as p over q in lowest terms, but then we're going to derive a contradiction. And this forces us to conclude that the square root of 2 cannot be rational. So we're going to use a proof by contradiction here. And so let's keep pushing through. So yeah, let's do that. So we're going to assume that the square root of 2 is rational. And so that means we've got, p over q, p and q are integers. That's what this means. The greatest common multiple, sorry, let's go back a step. The greatest common multiple of p and q is 1. That just means it's in lowest terms. So if we square both sides, we square the left-hand side, we get 2. And so we get p squared on q squared. Multiply both sides by q squared. So we get p squared equals 2q squared. So this equation is, what we need to keep at the heart of our proof here. And now we use what's called prime factor tree to analyze both sides. So let's see what those factor trees would look like. And here they are. So if we look at the first side first, which is the left-hand side. So we've got p squared. And so whenever the prime factor p, whatever prime factors p has, we know that has to be an even amount. And let's just finish that off there. So p squared has an even number of factors. And that's sort of what we were talking about before with the number 36. Because it's a perfect square, the sort of factor tree is symmetrical. Well, that's how I think about the whole thing. Everything here is sort of symmetrical. Because even if you break it down, you're going to have the same thing on both sides because it's a perfect square. Because p squared is p times p, and then you can keep going. But no matter what you do, you're going to end up with an even number of prime factors. So I think that's interesting. And so maybe you're starting to get a feel of how we're going to get some sort of contradiction here. But if we did the right side now, it's going to look like this, isn't it? Here's what our factor tree would look like. For the right side, 2q squared. Q squared has all even exponents. But we've got this extra factor of 2. So just on the the q squared part, we know that that's an even, same as before, that's going to have an even number of factors, but then we've got this extra 2 because obviously 2 is clearly a factor of 2q squared. So we clearly have an odd number of factors overall. But we know from before that q squared equals p squared equals 2q squared. So clearly we've got a contradiction. And so this is the heart of our proof. So we're saying we assume that p squared equals 2q squared, but what's called the fundamental theorem of arithmetic. Every integer greater than 1 has a unique prime factorization. However, p squared and 2q squared are the same number, so they must have the same prime factorization. But we just showed p squared has an even number of prime factors and 2q squared has an odd number of prime factors. So we have a contradiction, because even is obviously not the same as odd. And so our assumption that the square root of 2 equals p on q must be false. Therefore, the square root of 2 is irrational.